right. Anyway, so I will just talk about one use of Bootstrap here. So the idea behind Bootstrap is very simple, right. So I have a large sample, right, I have a large sample of data. So what I am going to do is I am going to sample from this data with replacement. Let us assume that the set S has n elements in it. So what I will do is I will sample from it another set S prime that also has n elements. Okay, does not sound like a big thing, right. I mean, if I do not sample with if I sample without replacement, I will essentially be duplicating it, but I am sampling with replacement. So what is the idea behind doing this?
If you take the average of all of them, it will cancel error.
No. So if you remember, I said that the assumption that we are making is that exactly the assumption that we are making is that the data is truly representative of the underlying distribution, right, in which case given the data, right, the best approximation I can construct to the underlying distribution is the discrete distribution, right, defined on this data, right. In one sense, if I do not make any other assumptions, all I can do is I can construct a discrete distribution on the data, right. So the probability of sampling this point x1 is equal to the number of times x1 appeared in my set S divided by the size of S, right. So how do I simulate this distribution? Sample from S with replacement. Does it make sense to people? Right. So I am going to assume that S, in some sense the set S is representative of the underlying data distribution, and I am going to simulate the underlying data distribution by using the discrete distribution formed by S. Right. So what do I mean by the discrete distribution? I do not know, maybe the underlying P is actually Gaussian or whatever, but my S has only n elements. So only these n points will have some non-zero probability of occurring. So that is what I mean by the discrete distribution. So I can just construct the discrete distribution from S and I will sample from that will give me S prime, right. So I will call it S1 prime, and like that I can do that multiple times to get right. I can go up till SL prime, right. I can do that, I can create many such samples, okay. So now what I do to get a bootstrap estimate of the classification error. So this kind of a sampling to produce this L subsets I have done is called bootstrap sampling, okay. So once I have derived such samples, I can find out the bootstrap estimate of the quantity that I want, right. So in this case error, so what will I do? I will train on S1 prime, right, and what will I test on? I will train on S1 prime and I will test on S minus S1 prime, right, because I am sampling with replacement, so some of the data points will get left out, right. So whatever gets left out I will test on that. So likewise I will train another classifier on S2 prime, right, using the same method. If I am using backprop for training, I will use backprop and train on S1 prime, okay, and test on S minus S1 prime. Likewise I will train on S2 prime and test on S minus S2 prime, likewise. So I will get how many estimates for the error? L estimates. I will take an average of that gives me the bootstrap estimate for the error, right. And you can show that the bootstrap estimate will have a lower variance than just the error estimate on just using S and just randomly splitting S into test and train, it will have a lower variance, right. So what again I want to be clear, what do I mean by lower variance here? If I give you another training data point of size n, right, and then you do the same thing, you do two estimates, one just train on the original set that is given to you and test on the test set once, or do this bootstrap estimate. Likewise, I give you another data point, data set of size n, another data set of size n, and so on and so forth. So now you will have two estimates for each of these. Okay, the second estimate will be more consistent than the first estimate. Okay, that is what I mean by lower variance. Okay, great. So that is a bootstrap estimate. Okay, so this is sometimes I forget the exact number. So
Not estimate of variability, it is estimate of error.
huh? It is estimate of the error, yeah, but it is some parameter that I am estimating about the whole process, that is why I said, right. So this is one way of estimating the performance, right, or thing. Right. I mean you can estimate anything you want on S1 prime, S2 prime, S3 prime, S4 prime, you can do whatever, right. You can estimate the variance of the data on S1 prime, just the variance of S1 prime, I am not talking about anything, right. You can do this for each of those L things and then you can have a bootstrap estimate of the variance, right. So you can do whatever statistics you want, you can measure on these L sets, right, and then you can call that the bootstrap estimate. Okay, so bootstrap is a very general technique, it is not just for error measurement. Okay. Yeah, so if you had been in a proper statistics course by now, you would have gotten into the variance reduction properties of bootstrap, and we could have shown some interesting results, right. But I am just going to tell you that yeah, the variance goes down, and you can see intuitively it goes down, and I will leave it at that. Okay. So roughly about 69% of the data, okay, on an average, right, 69% of the data will be in S1 prime, and the remainder 63% of the data, sorry, 63 will be in S1 prime and remainder will be in the test data, right. So this is also sometimes called that I forget 0.632 bootstrap or something like that, because sampling with replacement leaves a certain fraction of the data in the sample and leaves another fraction of the data in the test set. Okay, so it's sometimes that fraction also denotes what bootstrap estimated is, right. You remember? Okay, great. So this is one way of doing it, and this works fine, provided I had a large enough sample to begin with, right. Provided I had large enough sample to begin with. So suppose your sample is smaller, okay. Suppose your sample was smaller, you do something called cross validation, k-fold cross validation. So what you do is you take your sample, okay, you divide it into multiple bins, and I divide it into k bins. Then now what I do, I train on some k minus 1 bins, and I test on the last bin, right. Is it clear? So I use the first k minus 1 bins as my training data and 1 bin as the test data. Next what I do, instead of using the last bin, I use the second last bin as the test data and everything else as the training data, right. Suppose I break this into k bins, I will have k different estimates, right, and I take an average of those, right. So which will give you a better estimate, bootstrap or cross validation? Depends, yeah. Okay, that's not the end of it though. You have to tell me what it depends on. Huh? Depends on the size of the data. I mean, if you have a sufficiently large sample that your bootstrap assumption is true, right? So you might get a better estimate with bootstrap, right? One of the nice things about cross validation is that every data point is in the test set at least once. Is it correct? exactly once, every data point is in the test set exactly once. So in some sense whatever number that you are reporting is essentially the average over your performance on the entire sample that has been given to you, right, entire sample that has been given to you, at some point you are using this. So there are a few caveats that you have to worry about. The first one is, what is k, right, and the second one is the actual process of creating folds. So what should be k? Five to 10, yeah, okay, yeah. So those are the numbers typically used, 5 or 10. Okay, those are the numbers typically used, and so depending on the number of folds you have, okay, you have stronger variance reduction properties. The more the number of folds, the more the variance reduction property, provided the folds are large enough, right. If you have k data points, there is no point in creating k folds, but people do. Okay, there is a very special kind of cross validation, I will come to that later, but I am just going to leave you with the short form of it. Okay, so we'll come to that. So which is exactly creating k folds if you have k data points. It's called leave one out. Leave one out cross validation. Okay, leave one out. That's what LOO stands for, right? That essentially means that you will train on n minus or k minus 1 data points and test on one data point. Okay. So in some cases, no. There are actually in cases where this actually gives you good estimates. Okay, and earlier a version of this was the one of the first. Don't ask me why it's called jackknife, but one of the earliest this kind of variance reduction technique used for parameter estimation, right, was called jackknife. Okay, jackknife is very similar to leave one out. Okay, so going back here, so I would recommend that don't split it into so many folds that you have very little data point left in each fold, right, and so the typical number don't go more than 10 folds, right. If you manage to get 10 folds out of your data, right, then you should just be happy, right, that gives you good enough variance reduction. So typically people when you report empirical results don't expect you to do more than 10 folds, right, but then if your data size is small, right, people end up doing only 5 folds, right. There are extraordinary cases even when your data size is not small, when you have to do fewer folds. Right. So let us think for a minute. Suppose I have I am solving a classification problem, right. So I have created these folds, right, and this is entirely of class 3, okay, and there is no class 3 in this data, right. See, you think this is odd? This can happen quite frequently if you are dumb about how you split your data. So the data has come to you sorted by class label. I will give you the class file sorted by class label and you do the 5-fold splitting by serial number, right. So what will happen is you will have all your class go into one fold, right, the other 4 folds will not have any data point of class 3. Now if you try to test on this, what will happen? Yeah, right, because you do not even know there exists class 3. Okay, in your training you did not even know there was class 3, so you are going to get 100% error, right. So how do you avoid that? Shuffle the data. In fact, I do better than that. I do what I call stratified sampling. Okay. So I am not going to make much progress today, so we will have to stop with cross validation. I have so much more that I need to talk about, we will do that next class. So stratified sampling. So stratified sampling essentially says that when you create the folds, try to make sure that the class distribution that you had in the original data is maintained, right. Suppose I have 5 data points of class 1 and 10 data points of class 2, right, and I am splitting it into 5 folds, right. I should make sure that there are 2 data points of class 2 and 1 data point of class 1 in every fold, right. So, the class distribution, the 2:1 ratio is maintained in every fold. Okay. So, this is called stratified sampling. So, this is something that you have to do. So, the recommendation is do 10-fold, then you do stratified sampling. And now, can you answer my question, why even though you have a lot of data, you might be forced to have smaller number of folds? Huh? Class imbalance, right. So, I might have very few data points of one class. What if I have only 10 data points of one class, right? If I do 10-fold sampling, 10-fold cross validation, right, I will essentially put one data point of that class into each fold. That might not be sufficient for me to get a good enough estimate, right. I might want to do a smaller number of folds, 5, maybe 3, right. Of course, there are other things which I could do, but this is some case where you might want to work with a fewer number of folds than what your data would support, right. So, if you want to have a more formal description of cross validation, bootstrap and leave one out and all of that, you are encouraged to read HASTE, right, the Elements of Statistical Learning book has very nice discussion on all of these things, right. So, right now I will stop here, right.